Okay, this is part 2 of 2 of section 6.1. So part 2 of 2 of section 6.1. In part 1, we were talking about projectile motion, but we were talking strictly if all my velocity was in the x or if it was all in the y. If I threw something straight up and down, or if I threw it off a cliff and then it falls an angle down. But what happens, for example, if I throw a ball? Think about it. Do you ever throw a ball directly at a 90-degree angle straight up or a 0-degree angle straight out? Heck no. That never happens. Rarely. All right? Think about throwing a football or a softball or a baseball. You're letting that go at an angle. Or if you think about a punter in football, and he punts the ball, he's punting that at an angle. So we have to figure out velocities for angles as well. So, problem solving. When you talk about solving problems where you have angles, objects launched at angles, you have to do a couple things. All right? First things first, we talked about this multiple times already. You have to divide things into your x and to your y. And that's really important. Once you have everything broken apart into x and y, you're going to be good to go. So just like when we talked about newtons and forces in the last chapter, if I have two people picking up signs, you broke everything into x and y and then you solved with a new triangle. You're not doing anything with triangles here, but you need to break it apart into your x velocity and your y velocity. Here's something. If I throw an object up and it takes 4 seconds from when I throw it up to when I catch it at the same level again, how high or how long does it take to get to its highest point? Exactly half the time. So if I throw a ball up in the air and I catch it and it comes back down and I catch it and took 4 seconds start to finish, at 2 seconds that ball is at its very highest peak. So you have to kind of remember that, because we will talk about that later. Right? Or if I'm punting a ball and my hang time was 5 seconds, at 2.5 seconds that ball was at its highest point. So it takes 2.5 seconds to rise, 2.5 seconds to fall. Those times are equal. And as always, we're ignoring air resistance even though we could have really large objects. So when we talk about solving for angles, solving for x velocity and y velocity, we have two really simple equations. Vx is equal to vi, the initial velocity, times the cosine of theta. And v, that should be vy, not yy, that should be vy, is equal to vi times the sine of theta. Now just a reminder, since we're using angles again, that your calculator is in degrees when you are solving for these problems. So keep that in mind. So Vx is equal to Vi times cosine of theta, and Vy is equal to Vi times sine of theta. So if we take that and we do a real problem here, and our problem ends up being a ball is launched at 4.77 meters per second at 66 degrees above the horizontal. So a ball is launched, we are almost kicking a ball, you could say, at 66 degrees. All right. How long did it take for the ball to land? Well, it's very similar to the problem that we did earlier in part 1. However, remember the first step. Before we do anything, we need to solve for Vx and we need to solve for Vy. So when we go ahead and do that, let's go and solve for Vx and Vy. So we know Vx is equal to Vy times the cosine of theta. Well, that's equal to 4.77 meters, meters per second. You just plug in a 4.77. That's equal to 4.77 times the cosine of 66 degrees. Vx in this problem ends up being 1.94 meters per second. We go ahead and we do the same thing for Vy. Vy is equal to Vi times the sine of theta. That's equal to 4.77 times the sine of 66 degrees. Multiply those together and Vy is equal to 4.36 meters per second. Now, we have established Vx and Vy. Our problem solving is exactly the same now. We want to solve for time. All right. Well, we have two equations to deal with that. We have x is equal to Vx times t, or we have y is equal to vyt plus 1/2 gt squared. So you have to look at your options again. Which one of these two equations is going to help me solve the problem? Do we have x? No. Nowhere in this problem was the x value given, and we can't solve for x, so that equation's out. Which means by default again, we're left with y is equal to vyt plus 1/2 gt squared. All right. We know y. And you're like, well, we don't know why. Think about it. If I kick a ball, all right, I'm going to kick it off the ground. Where is that ball going to land? The ground. Is there any height change in that? No. So y is 0. If I kick a ball and it goes up in the air and comes back down, it's going to land at the same height I kicked it, unless I'm kicking it off of a hill. Yeah, or into a tree and it gets stuck in a tree or something like that. But though it's gonna come up and it's gonna come down. So we can assume that. All right. We have Vy. We just solved for Vy and we want to know T. We're solving for T and we have G. So let's go ahead and plug everything in. Y is 0. That is equal to Vy, which is 4.36 times T plus 1/2 g 9.8 t squared. When we clean up this equation, we're left with 0 is equal to 4.36 t plus 4.9 t squared. Well, how do we solve for t? We're stuck with a little bit of algebra here. We're going to pull a t out of the equation. We're going to pull a t out, and we're left with 4.36 plus 4.9 t now. We factored it out. We factored out a t. Well, t can equal 0, or, so t could equal 0 here, or what we solve for t here. There's two possible answers for t. But can time equal 0? Absolutely not. So what we're really set up with is 0 is equal to 4.36 plus 4.9 t. And you subtract 4.36 is equal to 4.9 t. We're dealing with time, so you're going to end up taking the absolute value of this negative number. And when you take 4.36 divided by 4.9, you're getting 0.889. Remember sig figs? We started with 2 because our angle was in 2. So we're going to end with 2, and our time ends up being 0.89 seconds. All right. That's the first question. All right. The second question, how high did the ball go? So we want to know why. So how high, we're talking about y values again. Well, we can solve for y. We have an equation for y. Y is equal to Vyt plus 1/2 gt squared. The same equation we just used, except one important thing. Remember, it takes half the time to rise and half the time to fall. So when an object is at its highest point, it's only at half its time. So we just solved that the ball is in the air for 0.89 seconds. Well, that means at its highest point, it was at half of 0.89, which is 0.445. So we're going to go ahead and we're going to solve for y using all the things that we knew. We know y is 4.36 times t, which is 0.445, because it's half of our value since we're at our highest point, plus 1/2 times 9.8 times 0.445 squared. Right. You go ahead and you add that all up, and you get y is equal to 2.9 meters. Sig figs, there's 2. So essentially, what we're doing here is we're taking the two equations we learned in part 1, our x and our y, right? And now we're applying our angles, which is our cosine and our sine, to solve for vx and vy. We combine those together, and we can use the two equations that we solved or used in part 1 to kind of help us out. So last couple things when we talk about trajectory. Remember again, every person sees it differently. Right? The trajectory is all dependent on your sight lines and your angle. It's very much like reffing basketball. When I ref basketball and I say, "Oh my God, I got fouled," well, you have a completely different angle on the play than I do, so you see things differently. The same thing applies for trajectories. Right? And always, we neglect air resistance. We are never going to talk about air resistance. So that is part 2 of section 6.1. We are taking angles and we are applying them together. You have an assignment on this later in the week.